When Max Planck began his investigations into the nature of radiation, he had no intention of revolutionizing physics. He was, in many ways, a conservative scientist who deeply admired the classical framework built by Newton, Maxwell, and Boltzmann. To him, the universe was a grand, logical machine governed by precise mathematical laws, a cosmos of certainty and continuity. Yet, history has a strange way of choosing its revolutionaries, and it chose Planck not because he sought chaos, but because he sought truth. The story of how Planck discovered energy quanta, the fundamental packets that underpin all of modern physics, is not merely a tale of equations and experiments. It is a story of intellectual struggle, philosophical humility, and the moment humanity first glimpsed the discrete nature of reality. At the end of the 19th century, physics seemed nearly complete. Many scientists confidently declared that the great mysteries of nature had been solved. Newtonian mechanics explained motion, Maxwell's equations described electromagnetism, and thermodynamics governed energy and heat. The prevailing belief was that everything could be understood through deterministic laws. If one knew the position and velocity of every particle, the entire future of the universe could, in principle, be predicted. Yet beneath this calm surface, a few persistent problems refused to yield. One of the most troubling was the so-called Blackbody radiation problem. A blackbody is an idealized object that absorbs all radiation that falls upon it and re-emits it depending only on its temperature. When such an object is heated, it glows, first red, then orange, then white as the temperature rises. Experimentally, scientists could measure how much light of each wavelength was emitted at various temperatures. But when they tried to explain this using classical physics, they ran into a paradox. According to classical theory, as the wavelength of light gets shorter, the energy radiated should increase without limit. This meant that a hot object should emit infinite energy at ultraviolet wavelengths, an absurd result later known as the ultraviolet catastrophe. Planck, working at the University of Berlin, took on this challenge in the 1890s. His goal was modest, to find a mathematical expression that matched the experimental data. For years, he approached the problem using the methods of classical thermodynamics and electromagnetic theory, but no formula would fit both the low and high frequency regions of the observed spectrum. The data, measured with increasing precision by experimentalists like Lummer and Pringsheim, mocked every theoretical curve. Yet Planck was not easily discouraged. He believed there must be a deeper law governing the interaction of matter and radiation, a law hidden within the statistics of microscopic oscillators. By 1900, after years of struggle, Planck decided to take an unconventional step. He drew upon the statistical methods of Ludwig Boltzmann, though he had long been skeptical of them. Boltzmann's work introduced the idea that entropy, a measure of disorder, was connected to the number of microscopic ways energy could be distributed among particles. Planck used this idea to describe how energy might be shared among the vibrating charges or resonators inside matter. But in doing so, he had to make one radical assumption. The energy of each resonator could not vary continuously, but only in discrete amounts proportional to its frequency. Mathematically, this meant that the energy E of a resonator was given by E equals NH, nu E equals NH backslash nu E equals NH nu, where n and n is an integer 0, 1, 2, 3, nu backslash none, u is the frequency of vibration, and HHH is a new fundamental constant, now known as Planck's constant. This was a breathtaking departure from classical physics. It implied that energy, which had always been considered continuous, could exist only in specific packets, or quanta. Planck himself did not fully realize the depth of what he had done. He viewed this quantization as a mathematical trick to fit the data, not as a statement about the actual nature of reality. Yet, when he used it to derive the spectral distribution of blackbody radiation, the result matched the experimental observations with stunning accuracy. On December 14, 1900, he presented his findings to the German Physical Society, a date now celebrated as the birth of quantum physics. To understand the magnitude of Planck's leap, one must appreciate the mindset of physics at that time. The idea that energy could be granular seemed as absurd as suggesting that space itself was made of discrete points. Classical physics was built on the assumption of continuity. Forces varied smoothly, waves oscillated seamlessly, and energy could take any value. Planck's formula broke that sacred continuity. It suggested that nature, at its most fundamental level, does not flow like water, but flickers like a strobe, jumping in tiny, indivisible steps. For Planck, the most unsettling part was not that the formula worked, but that he could find no physical justification for it within existing theory. He was a reluctant revolutionary, driven by necessity rather than vision. He once described the moment as an act of desperation. But desperation in the hands of a genius can become revelation. Planck's constant, the proportionality factor HHH, turned out to be astonishingly small, about 626 times 10 minus 34 J backslash C dot 626 backslash times 10 minus 34 backslash text JS 626 times 10 minus 34 J backslash C dops. This meant that the quantum nature of energy was invisible at the human scale, but dominant at the atomic one. The universe, it seemed, was smooth to us only because we were too large to see its graininess. The implications of this discovery were not immediately recognized. Many physicists treated Planck's constant as an arbitrary fudge factor, useful for solving one particular problem but irrelevant to the broader picture. Even Planck himself was uneasy with the radical meaning his own theory implied. Yet within a few years, his quantum idea began to ripple outward. In 1905, Albert Einstein took Planck's hypothesis seriously and extended it. While Planck had quantized the energy of matter oscillators, Einstein suggested that light itself was made of quanta, discrete packets later called photons. He used this idea to explain the photoelectric effect, in which light knocks electrons out of metal surfaces. Classical theory said the energy of ejected electrons should depend on the intensity of light, but experiments showed it depended on frequency instead. Einstein's quantum explanation not only solved the puzzle, but earned him the Nobel Prize. It was also the first clear indication that Planck's mathematical trick reflected a fundamental truth about the universe. Planck, though cautious, recognized the brilliance of Einstein's reasoning. He became one of the first major scientists to support Einstein's early work, even when others dismissed it. Still, Planck remained philosophically uneasy with the idea that light itself was quantized. His conservative nature resisted the thought that the wave theory of light, so beautifully established by Maxwell, might not be the whole story. He spent much of his later life trying to reconcile quantum discontinuity with classical harmony, a reconciliation that still challenges physicists today. The historical context of Planck's discovery is also crucial. Around the same time, the scientific community was wrestling with the meaning of entropy, probability, and the microscopic nature of matter. Boltzmann's statistical view of thermodynamics had been controversial. Many physicists doubted the existence of atoms altogether. Planck's acceptance of Boltzmann's methods marked a philosophical turning point, a recognition that the microscopic world might follow laws fundamentally different from those governing macroscopic phenomena. In this way, Planck not only discovered energy quanta, but also laid the groundwork for the statistical interpretation of physical reality. The beauty of Planck's approach lay in its simplicity. He began with empirical data, sought a formula to match it, and let mathematics lead him where intuition would not dare. His resulting Planck radiation law elegantly combined experimental accuracy with theoretical novelty. It described how the intensity of radiation varied with frequency and temperature, predicting a curve that rose, peaked, and then fell precisely as experiments showed. More importantly, it bridged the gap between two earlier, conflicting laws: Wien's law, accurate for high frequencies, and the Rayleigh-Jeans law, accurate for low frequencies. The Planck law was the first to unite them, demonstrating that both were merely approximations of a deeper quantum truth. Philosophically, Planck's discovery cracked open the door to a new world. It hinted that the universe might be discrete at its core, governed not by smooth causality, but by statistical rules. It suggested that certainty was an illusion, that even the most fundamental quantities of energy come in steps. This was the seed from which the entire quantum revolution would grow. In later decades, this seed would bloom into quantum mechanics, a theory that describes how particles behave in terms of probabilities and wave functions rather than deterministic paths. But it all began with Planck's humble realization that energy, like matter, might have an atomic structure. Without his constant HHH, the equations of modern physics, from Schrödinger's wave equation to Heisenberg's uncertainty principle, would collapse. Planck's quantum was not merely a numerical parameter. It was the thread connecting all microcosmic behavior. The human side of Planck's journey is equally profound. He was not a young rebel, but a middle-aged professor, deeply rooted in classical ideals. His discovery emerged not from wild speculation, but from methodical persistence and intellectual honesty. When confronted with data that contradicted theory, he did not distort the data. He changed the theory. That act, simple yet courageous, marks the essence of scientific progress. It shows that revolutions in thought are often born not from chaos, but from discipline, not from imagination alone, but from fidelity to truth. After 1900, Planck's life was filled with both triumph and tragedy. His scientific achievements brought him fame, yet his personal life was scarred by loss, the deaths of his children, the destruction of his home during World War II, and the execution of his son for resisting the Nazi regime. Through it all, Planck held fast to his belief in the moral and rational order of the universe. His faith in reason and his reverence for nature's laws never wavered. This quiet strength perhaps explains why his discovery carried such depth. It was born of a mind seeking harmony even amid uncertainty. From a modern standpoint, we can now see how Planck's quantization underlies nearly every aspect of contemporary science and technology. The energy quanta he proposed govern the behavior of electrons in atoms, the emission of photons in lasers, the functioning of semiconductors, and the information processes of quantum computers. Every digital screen, solar cell, and MRI scanner operates on principles that trace back to Planck's insight. The world of the 21st century is, quite literally, a quantum world, built on the foundation he laid. Yet the philosophical consequences are as significant as the practical ones. Planck's discovery forced humanity to rethink what reality means. It shattered the comforting notion of a predictable, clockwork universe and replaced it with one governed by probabilities, discontinuities, and fundamental limits. It revealed that at the smallest scales, nature does not behave like a machine, but like a symphony of chance and pattern, a harmony that only statistics can describe. Planck himself remained a modest man. When he later received the Nobel Prize in 1918 for his discovery of energy quanta, he accepted it not as a personal triumph, but as a step forward for human understanding. He often emphasized that his work was merely the beginning, not the end, of the journey. Indeed, he could not have imagined how far that journey would go to the quantum mechanics of Heisenberg and Schrödinger, to quantum field theory, to the discovery of particles that wink in and out of existence. All of these trace their ancestry to that cold December day in 1900, when a reluctant German physicist dared to suggest that energy comes in pieces. Looking back, we can appreciate how extraordinary this intellectual leap truly was. Planck stood at the boundary between two worlds, the classical and the quantum, and bridged them with a single constant. He did not discard the old order, he extended it. His quantization did not destroy continuity, but redefined it at a deeper level. Energy was still conserved, but it flowed in discrete steps rather than in an unbroken stream. This subtle shift in perspective turned out to be one of the most revolutionary in the history of science. Planck's discovery also marked a transformation in the methodology of physics itself. It introduced a new style of thinking, one that accepted the limits of human intuition and embraced abstraction. The quantum, after all, could not be seen or touched. It was inferred through mathematics. This reliance on symbols and probabilities would become a hallmark of 20th century physics. It required scientists to trust equations over experience, to believe that nature's behavior at invisible scales might defy common sense. Planck paved the way for that intellectual courage. In a sense, his discovery was as much philosophical as it was scientific. It redefined the meaning of reality. What does it mean for energy to exist only in quanta? Does the universe operate by chance or by law? Is continuity merely an illusion born of human perception? These questions still echo in physics and philosophy alike. Planck may not have answered them, but he gave us the vocabulary to ask them. The birth of quantum physics, then, was not just the beginning of a new scientific theory. It was the beginning of a new human world view. It invited us to see ourselves as participants in a probabilistic universe, to accept uncertainty not as ignorance, but as an intrinsic property of existence. It humbled us by showing that even the simplest phenomena, the glow of a heated iron, the color of the stars, depend on principles that defy classical logic. Planck's quanta were not merely units of energy. They were symbols of a deeper truth, that nature, in its core, is both orderly and unpredictable, both structured and mysterious. His discovery remains a testament to the power of persistence, reason, and the willingness to question even the most established beliefs. And thus, with the introduction of energy quanta, the quantum age was born quietly, almost reluctantly, from the mind of a man who sought order but found mystery instead. Max Planck, in unraveling one of the simplest problems of physics, had unknowingly unraveled the very fabric of reality. The true measure of a discovery lies not only in the equations it produces, but in the revolutions it ignites. After Planck's revelation of the energy quantum, physics could never return to its former simplicity. The idea that energy is emitted or absorbed in discrete amounts was the spark that set the scientific world ablaze, inspiring a century-long exploration that continues today. To grasp the magnitude of this transformation, we must trace how Planck's modest proposal spread, evolved, and reshaped both science and philosophy. When Planck published his Blackbody radiation formula in 1900, he believed it to be a technical refinement, a patch on the fabric of thermodynamics. Yet, within 5 years, his assumption of energy quanta began to ripple outward in unexpected ways. Einstein's 1905 paper on the photoelectric effect took Planck's quantization and applied it not to matter but to light itself. This bold move suggested that electromagnetic radiation came in bundles, later called photons, each carrying an energy E equals h nu, E equals h backslash nu, E equals h nu. It was a daring inversion of Planck's cautious stance, and it immediately explained why light of lower frequency, regardless of intensity, could not eject electrons from metal surfaces. In that single stroke, Einstein transformed Planck's mathematical convenience into a physical reality. Planck at first resisted this interpretation. He admired Einstein's intellect, but could not accept that the wave theory of light, confirmed by interference and diffraction, could coexist with a particle description. Yet nature forced acceptance. As experiments accumulated, it became clear that light exhibited both particle-like and wave-like properties. This paradox would become the heart of quantum theory. The wave-particle duality revealed that the universe does not fit neatly into human categories. Radiation and matter share a strange unity. Particles act like waves, and waves behave like particles. The idea soon extended to matter itself. In 1924, Louis de Broglie proposed that if light has a dual nature, then particles of matter must have it as well. His hypothesis that electrons possess a wavelength, lambda equals h/p backslash lambda equals h/p lambda equals h/p, where ppp is momentum, opened a new frontier. Within a few years, Davison and Germer confirmed electron diffraction, and the concept of the matter wave became an experimental fact. The world of Planck's quanta had expanded from energy to matter, uniting everything under a single quantum framework. The mathematical language of this new realm emerged through the works of Werner Heisenberg, Erwin Schrödinger, and Paul Dirac in the mid-1920s. Heisenberg's matrix mechanics and Schrödinger's wave mechanics, though seemingly different, described the same physical reality, a probabilistic world governed by Planck's constant. At the heart of every equation lay the discreteness that Planck had first glimpsed. The Schrödinger equation, I2, 1's 0, f delta psi delta t equals h psi backslash h, bar backslash frac backslash partial backslash psi backslash partial t equals backslash hat h backslash psii letter 2, 1's 0, f delta t delta psi equals h psi, could not exist without the tiny constant hhh that sets the scale of quantum effects. It was the universal signature of Planck's discovery. Heisenberg's uncertainty principle, formulated in 1927, deepened the philosophical consequences. It stated that one cannot simultaneously know a particle's position and momentum with arbitrary precision. Deltax delta greater or equal to letter 2, 1 0 f2, backslash delta x backslash delta p backslash g backslash frac backslash h, bar 2, deltax delta greater or equal to 2 letter 2, 1 0 f. This was not a limitation of instruments but a fundamental property of nature. The world was no longer deterministic but inherently probabilistic. Planck's constant, once a small numerical detail, had become the very measure of uncertainty in the universe. It defined the boundary between the classical and the quantum, between predictability and indeterminacy. The shift from determinism to probability was profound. Classical physics had promised certainty. Given initial conditions, the future was fixed. Quantum physics replaced that comfort with statistical inevitability. Events could only be described in terms of likelihoods. For Planck, who cherished order, this was unsettling. He had introduced the quantum unwillingly, and now it was dismantling the deterministic cosmos he revered. Yet, in the broader sense, his discovery expanded the notion of order. Nature's laws were still exact, but they governed probabilities rather than certainties. Reality itself had become a tapestry woven of potentialities. The next great leap was the recognition that Planck's quanta applied not only to isolated atoms, but also to the forces that bind them. Quantum electrodynamics (QED), developed by Dirac, Feynman, and others in the 1930s-1940s, described how light and matter interact through the exchange of photons. Every flicker of light, every chemical bond, every electronic device depends on this quantum exchange. The predictions of QED match experiment to extraordinary precision, 1 part in a trillion, all thanks to Planck's constant, which sets the scale of every calculation. Technological revolutions followed. The invention of the transistor in 1947 relied on understanding quantum behavior in semiconductors. The laser, discovered in the 1960s, depends on the quantization of light energy levels. MRI scanners, quantum dots, LEDs, and solar cells all exploit Planck's principle that energy changes in discrete steps. Even the atomic clock, our ultimate time standard, measures frequency directly tied to Planck's constant. The world that began as a theoretical curiosity has become the foundation of modern civilization. Yet, beyond technology, Planck's discovery reshaped human philosophy. It challenged the notion of a passive observer standing outside reality. In quantum mechanics, the act of observation affects the outcome, a concept encapsulated in the Copenhagen interpretation developed by Niels Bohr and Heisenberg. The observer and the observed are intertwined. Measurement collapses possibilities into actuality. This idea blurs the boundary between subject and object, echoing Planck's later reflection. Science cannot solve the ultimate mystery of nature, because we ourselves are part of nature. His constant HHH became not only a numerical limit, but a metaphysical one, defining the horizon of what can be known. As the 20th century progressed, physicists sought deeper unification. They discovered that all known forces, except gravity, could be described by quantum field theories built upon Planck's constant. These culminated in the Standard Model, a masterpiece of symmetry and precision. Yet gravity, governed by Einstein's general relativity, resisted quantization. The quest to merge the two, to formulate a quantum theory of gravity, remains the grand challenge of physics. Intriguingly, Planck's constant again appears at the heart of this search, combined with Newton's gravitational constant g and the speed of light c to form Planck its natural scales, length, time, and energy. These define the so-called Planck scale, the realm where quantum effects of gravity become significant and where space-time itself may become discrete. In that sense, Planck's name and his constant set the ultimate boundaries of physical reality. Philosophically, the discovery of quanta invites reflection on the nature of continuity and change. If energy, matter, and even space-time are quantized, does continuity exist at all? Or is smoothness merely an illusion produced by averaging over countless tiny jumps? The question extends beyond physics to metaphysics, art, and consciousness. The quantum world suggests that discreteness underlies every appearance of flow, that music, color, and motion arise from imperceptible steps of energy and time. Planck's insight thus connects scientific reasoning with ancient philosophical intuitions about the granular structure of existence. Planck himself never abandoned his belief in a rational cosmos. He saw the quantum not as chaos, but as a deeper order beyond immediate comprehension. To him, the constancy of HHH testified to a fundamental harmony underlying apparent randomness. Even as younger physicists embraced indeterminacy, Planck maintained that the universe remained lawful and intelligible, even if its laws exceeded human intuition. His attitude embodies a profound scientific humility, the recognition that truth may be stranger than imagination, but is never meaningless. The cultural impact of Planck's discovery also deserves attention. Quantum theory changed the vocabulary of modern thought. Words such as quantum leap, uncertainty, and probability entered everyday language, influencing psychology, economics, and even literature. Artists and writers found inspiration in the idea that reality is not fixed but fluid, that observation and interpretation shape what is seen. The quantum became a metaphor for creativity, ambiguity, and possibility. All of this stems from the tiny constant HHH, a number once scribbled in a notebook by a man seeking to fit data. The philosophical descendants of Planck's work include information theory and quantum computation. In these fields, the fundamental unit is not energy but information, yet both are measured by discrete quantities. A quantum bit qubit can exist in superposition, embodying multiple states at once, a concept rooted in the same discreteness that Planck introduced. Quantum computers promise to solve problems impossible for classical machines, harnessing the probabilistic nature of the micro-world. Every qubit, every entangled pair, operates according to Planck's constant. Thus, even the future of technology still echoes the birth of quantum physics in 1900. The spiritual dimension of Planck's journey should not be overlooked. He saw science and faith as complementary pursuits, both seeking order and meaning in the cosmos. In lectures and writings, he spoke of a divine rationality underlying the laws of nature. For Planck, discovering the quantum was not a denial of harmony, but its revelation in a new form. He once said, "The scientist is a man who does not aim at immediate results. He does not expect that his advanced ideas will be readily accepted. His duty is to lay the foundation for those who are to come." This humility and foresight characterized the man who unknowingly set humanity on a century-long journey into the heart of reality. In hindsight, we can view Planck's quantization as the first bridge between the visible and the invisible. It revealed that macroscopic phenomena, light, heat, color, emerge from microscopic acts of emission and absorption, each governed by discrete laws. It also hinted that human perception is limited, that continuity is a convenient illusion. Every photon we see, every sensation of warmth, is the collective whisper of countless quanta. The universe speaks in the language of Planck's constant. Today, experiments probe ever deeper into this quantum domain. Physicists entangle particles across kilometers, teleport quantum states, and cool atoms to near absolute zero to study their quantized motions. Each of these feats confirms and extends Planck's insight. At the same time, the quantum world remains bewildering. Questions abound. Does reality exist before measurement? Can multiple universes arise from quantum choices? Are we ourselves quantum systems whose consciousness emerges from entanglement? These debates trace their ancestry to that single moment when Planck dared to quantize energy. From a broader historical lens, Planck's discovery illustrates the evolution of human knowledge. Every great scientific revolution begins with an anomaly, a fact that refuses to fit. The Blackbody radiation curve was such an anomaly. Instead of ignoring it, Planck faced it. His courage to question the assumptions of continuity transformed a minor problem in thermal physics into the foundation of a new era. The lesson is timeless. Progress is born when humility meets persistence. As the 21st century advances, physicists pursue quantum gravity, string theory, and loop quantum cosmology, all attempts to extend Planck's vision to the structure of spacetime itself. These theories predict that space and time may come in Planck-sized grains, the smallest possible units of existence. If confirmed, this would mean that Planck not only discovered the quantum of energy, but also foreshadowed the quantum of everything. The Planck length 1, 6 times 10 minus 351, 6 times 10 minus 35 1, 6 times 10 minus 35 m, and Planck time 5, 4 times 10 minus 4, 145, 4 times 10 minus 44 5, 4 times 10 minus 44 s, mark the edge of our cosmic understanding where the smooth fabric of spacetime dissolved into quantum foam. In that sense, the name Planck defines the very limits of knowledge. The continuing influence of his discovery cannot be overstated. Every university physics course begins with Planck's radiation law. Every quantum theory still carries his constant. His work stands as one of the few intellectual pillars on which modern science rests, alongside Newton's laws and Einstein's relativity. And yet, unlike those grand theories, Planck's quantum principle did not provide a full picture. It opened a mystery. It told us that the universe is quantized, but not why. That unanswered why fuels physics to this day. Reflecting on Planck's legacy invites a final philosophical meditation. The quantum world is not a realm apart from ours. It is our world seen truly. We live within Planck's domain, every heartbeat, every photon, every atom dancing to the rhythm of discrete energy. The discovery that energy comes in quanta teaches a profound lesson about knowledge itself. That truth often appears first as paradox, that understanding grows from the courage to doubt. Planck's quanta remind us that reality may be fragmented, yet it forms a coherent whole. Max Planck once wrote, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but because its opponents eventually die and a new generation grows up that is familiar with it." This humble observation captures the slow revolution his own discovery inspired. Over the decades, the quantum theory he birthed became the bedrock of all modern physics. The opposition faded, but the wonder remained. Thus, the story of Planck's energy quanta is not merely the story of a constant or a formula. It is the story of humanity's encounter with the limits of intuition and the beginning of a deeper dialogue with nature. By quantizing energy, Planck invited us to recognize that the universe is at once knowable and mysterious, logical yet elusive. His work unveiled a cosmos built not of continuous waves, but of discrete notes, a symphony whose score is written in quanta. More than a century later, as we peer into quantum computers, teleportation experiments, and the cosmic microwave background, we still hear the echo of that first quantum. Each discovery, each breakthrough, is a variation on Planck's theme. The constant he introduced has become the heartbeat of the universe, the rhythm by which all matter and energy move. His discovery truly marked the birth of quantum physics, the dawn of a new way of seeing, knowing, and being. For centuries before Max Planck's discovery, science was guided by the belief that the universe operated like a perfectly predictable machine. Every motion, every force, every event followed from fixed, unchanging laws. If one could know the present state of the universe with perfect precision, the position and momentum of every particle, then one could, at least in principle, predict the entire future and retrodict the entire past. This view, known as classical determinism, was not merely a scientific principle, but a philosophical creed. It defined the spirit of the Enlightenment and shaped the way humanity understood both nature and itself. It was the vision of Isaac Newton that first gave determinism its mathematical foundation. In the 17th century, Newton's Principia Mathematica revealed that the same laws governing falling apples also govern the motion of planets and stars. The universe, once thought to be ruled by divine whim or mysterious essences, now appeared as a harmonious system of cause and effect. Every action had a reaction, every motion could be calculated, every future could, in principle, be foreseen. Pierre-Simon Laplace, a French mathematician and philosopher, later gave this world its most precise formulation. He imagined an intelligence, later called Laplace's demon, that, knowing all forces and positions at one instant, could predict the entire course of the universe. For such an intelligence, he wrote, nothing would be uncertain. This vision was intoxicating. It promised that the universe was not arbitrary but knowable, not chaotic but ruled by immutable laws. It also shaped human philosophy, giving rise to the idea that free will itself might be an illusion, that our thoughts and choices, like the motions of planets, were determined by prior causes. The success of classical mechanics seemed to confirm this. Every mechanical system, from the swing of a pendulum to the orbit of Mercury, could be described by differential equations whose solutions unfolded deterministically from initial conditions. By the 19th century, this deterministic ideal had spread to all areas of science. James Clerk Maxwell's equations unified electricity, magnetism, and light into a single electromagnetic theory, describing waves that propagated through space with mathematical precision. Thermodynamics and statistical mechanics, though introducing probabilities, were still understood as reflecting ignorance, not indeterminacy. The probabilities described our lack of knowledge of microscopic details, not any fundamental randomness in nature. The world itself was assumed to be entirely lawful and predictable. It was in this seemingly complete and confident world that the seeds of quantum physics were sown. When Max Planck, in 1900, discovered that energy was emitted and absorbed in discrete quanta, he did not immediately realize that he had opened a door that would lead to the destruction of determinism. His quantum assumption was initially a technical fix to an experimental problem, not a philosophical revolution. Yet the consequences of his discovery, amplified by the work of Einstein, Bohr, Heisenberg, and Schrödinger, would soon overturn the very foundation of classical certainty. The first cracks in the deterministic edifice appeared when Einstein's theory of light quanta explained the photoelectric effect in 1905. According to this idea, light was not a continuous wave but a stream of particles, each carrying a discrete quantum of energy. When a photon hit an electron in a metal, it transferred its energy instantaneously, ejecting the electron if the energy exceeded a certain threshold. The process was inherently statistical. Given a number of photons, one could predict how many electrons would be emitted on average, but not which specific photon would eject which electron. The event of emission was probabilistic, not deterministic. This was unsettling, but the real upheaval began 2 decades later. In the 1920s, quantum mechanics emerged as a comprehensive theory of the microscopic world, and with it came a new and radical interpretation of reality. The central figure in this transformation was Werner Heisenberg, who in 1925 formulated matrix mechanics, followed by Erwin Schrödinger's wave mechanics in 1926. At first, these seemed like different mathematical languages, but they soon proved equivalent. Both described the behavior of electrons, photons, and atoms not as precise trajectories, but as waves of probability. In classical physics, a particle's position and momentum could, in principle, be measured exactly and simultaneously. In quantum physics, this is impossible. Heisenberg's uncertainty principle expressed this limitation quantitatively. The more precisely one knows a particle's position, the less precisely one can know its momentum, and vice versa. This is not due to measurement error. It is an intrinsic feature of nature. The world itself is built upon uncertainty. At the heart of this new world, lies the wave, function, usually denoted by the Greek letter psi/psi. Schrödinger's equation describes how this wave, function evolves over time, not deterministically in the sense of definite outcomes, but deterministically in terms of probabilities. The wave function gives the likelihood of finding a particle in a certain state when measured. Yet, until a measurement is made, the particle does not have a definite position or momentum. It exists in a superposition of possibilities, all potential outcomes coexisting until observation collapses the wave, function into one specific reality. This notion was deeply troubling to the pioneers of the new theory. Even Einstein, who had helped launch the quantum revolution, recoiled from its implications. God does not play dice with the universe, he famously protested, rejecting the idea that chance could govern fundamental events. To Einstein, randomness was a sign of an incomplete theory, a placeholder for hidden variables that, if known, would restore determinism. But experiments, especially those inspired by John Bell's theorem in the mid-20th century, have shown that quantum indeterminacy is not an illusion. Nature truly behaves probabilistically at its core. In the quantum framework, the future is not a single predetermined path, but a spectrum of possibilities. The outcome of any measurement cannot be known until it happens, and even then, it arises from probabilities rather than certainties. This is not ignorance but fundamental reality. The world, at its most basic level, is a statistical ensemble of events. Every electron, every photon, every atom behaves according to probability amplitudes. Determinism, so long the bedrock of physics, gives way to a probabilistic vision of nature. The philosophical shift this represents is profound. Classical determinism assumed that nature was a closed system of causes and effects, that the universe was like a vast clock whose gears turned with perfect precision. Quantum physics replaced this with a universe of potentialities, in which observation itself becomes a creative act. Measurement no longer reveals pre-existing properties, it helps bring them into being. The observer and the observed are intertwined in a subtle dance of probability and realization. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, articulated this new vision most clearly. According to Bohr, it is meaningless to talk about the properties of a system, such as position or momentum, in the absence of measurement. Reality at the quantum level does not exist in the same way it does at the macroscopic level. Instead, it exists as a set of potential outcomes described by the wave function. The act of measurement selects one of these possibilities. Thus, Probability is not merely a tool for dealing with ignorance, but a fundamental aspect of existence. For Planck, who had begun this revolution unwillingly, such an interpretation would have been disquieting. He sought continuity and order, not chance and indeterminacy. Yet his discovery forced physics toward a new philosophy. The quantum theory that grew from his constant replaced the Newtonian image of a mechanical universe with one governed by probability waves, statistical laws, and fundamental uncertainty. The transition from determinism to probability can be seen as a shift in the very language of science. In classical physics, we asked, what is the exact state of the system? In quantum physics, we ask, what is the probability of finding the system in a given state? This change in question reflects a change in world-view. The universe is no longer a book already written, but a story that unfolds through interactions, measurements, and possibilities. The consequences of this shift extend far beyond physics. In philosophy, it has revived debates about free will, causality, and the nature of reality. If the universe is probabilistic, perhaps there is room for spontaneity, creativity, and choice within its fabric. In mathematics, it has deepened our understanding of randomness and information. In technology, it has led to quantum computing, quantum cryptography, and other fields that rely on harnessing probability rather than eliminating it. The move from determinism to probability did not abolish lawfulness, it redefined it. The equations of quantum mechanics are still exact and deterministic in describing how probabilities evolve. What they do not determine are specific outcomes of measurements. The laws govern the evolution of possibilities, not the realization of a single result. This subtle balance between order and randomness, between mathematical precision and physical indeterminacy, defines the modern understanding of nature. To see how this manifests, consider the double-slit experiment, one of the most famous illustrations of quantum behavior. When particles such as electrons or photons are sent toward two slits and not observed, they form an interference pattern on a screen, as if each particle were a wave passing through both slits simultaneously. But when we observe which slit the particle passes through, the interference pattern disappears, and the particles behave as if they took one definite path. The outcome depends on whether the system is measured, a demonstration of how probability and observation shape physical reality. This experiment encapsulates the essence of the quantum world. Reality is not fixed until observed, and even then, it reflects the probabilistic nature of underlying laws. The deterministic picture of Newton, where particles follow predictable trajectories, is replaced by a probabilistic tapestry of potentialities. Every event, from the decay of an atom to the behavior of electrons in a semiconductor, is governed by quantum probability distributions. Thus, the rise of the quantum world represents not the abandonment of science's precision, but the deepening of its honesty. It acknowledges that certainty is not the same as truth, that predictability is not the same as understanding. Planck's constant HHH symbolizes this new humility, a recognition that even in the most exact sciences, there are limits beyond which determinism cannot reach. In this sense, Planck's discovery did more than change physics. It transformed humanity's conception of knowledge itself. The universe is not a static mechanism, but a living web of possibilities, a dynamic interplay of chance and necessity. Quantum mechanics, born from Planck's energy quanta, replaced the rigid chains of causality with a dance of probabilities, a dance that continues to inspire both awe and inquiry. At the deepest level, the rise of probability in physics forced scientists to accept that nature is not simply an intricate clockwork of causes, but a field of potential events. Each event emerges only when conditions make it possible, a dance between what can happen and what does happen. In this sense, the quantum world is a vast sea of possibilities, and observation acts like a pebble dropped into that sea, creating ripples that solidify one outcome while excluding countless others. This idea was not merely poetic. It was born from rigorous mathematics and repeatedly confirmed by experiment. Heisenberg's uncertainty principle, Schrödinger's wave equation, and Bohr's complementarity all converged on one truth. The physical universe, at its roots, is statistical. It does not unfold as a line, but as a web, where each thread represents a probability. The observer's act of measurement cuts through the web, selecting one strand out of many. That act is irreversible. The measured result becomes history, while the unchosen possibilities fade into non-existence. To many early physicists, this picture was almost unbearable. Einstein famously called quantum mechanics incomplete, insisting that hidden variables must exist to restore causality. He collaborated with Boris Podolsky and Nathan Rosen in 1935 on the famous EPR paradox, arguing that quantum theory allowed spooky action at a distance, which seemed impossible. Their argument challenged Bohr's interpretation and demanded that a deeper, deterministic layer exist beneath quantum probability. Decades later, however, John Bell's theorem showed that if local hidden variables existed, they would lead to measurable differences from the predictions of quantum mechanics. Experiments, most notably those by Elaine Aspect in the 1980s and Anton Zeilinger's group in the 1990s and 2000s, confirmed that quantum predictions were correct. Entangled particles behaved in ways that violated local realism, but preserved internal consistency. Nature, it seemed, was non-local and probabilistic. There were no hidden variables restoring classical certainty. The dice that Einstein rejected were indeed part of the fabric of the universe. This realization did not mean that chaos ruled. On the contrary, quantum probability follows strict mathematical laws. The Schrödinger equation predicts how the wave function evolves deterministically, but what it evolves is not a single outcome, rather a pattern of probability amplitudes. When a measurement occurs, the probabilities collapse into a definite result. Thus, determinism survives at one level the evolution of probability distributions, but disappears at another the occurrence of individual events. The new framework unites order and chance in a subtle equilibrium, law without predictability, structure without preordination. This balance is best illustrated in the phenomenon of quantum interference. When two probability waves overlap, they can reinforce or cancel each other, much as physical waves do. Yet here, it is the probability of outcomes that interferes. This means that the universe keeps track of all possible paths a particle can take, not physically, but in terms of mathematical probability, and the observed result is the sum of those possibilities. Richard Feynman later turned this insight into his path integral formulation, where a particle's behavior results from summing over every conceivable path weighted by a phase factor. Each path contributes, but only probabilistically. Determinism is replaced by an elegant calculus of potentiality. The conceptual consequences ripple outward. In classical mechanics, causality is linear. Event A causes event B. In the quantum world, causality becomes non-local and contextual. The outcome of a measurement may depend on how an experiment is set up, even when the setup is chosen after the particles have separated. This is the essence of entanglement, a feature that Einstein called spooky. Two particles that once interacted remain connected in their probability states no matter how far apart they are. Measuring one instantly determines the state of the other, not by sending a signal faster than light, but because both are described by a single, shared wave function. To many, this seems to imply that information or influence travels instantaneously, violating relativity. But in fact, no usable information is transmitted faster than light. Rather, the correlations are global features of the quantum system. The universe, at the fundamental level, is not made of isolated pieces, but of relationships, probabilities intertwined across space and time. The old deterministic picture of self-contained particles has given way to a networked cosmos of entangled probabilities. This probabilistic reality does not mean that everything is random. It means that randomness operates within boundaries defined by laws. The rules of quantum mechanics constrain probabilities with extraordinary precision. The decay rate of uranium atoms, the spectral lines of hydrogen, the tunneling probabilities of electrons all follow exact statistical patterns that can be predicted with astonishing accuracy. Thus, quantum probability is not the absence of order, but a higher form of order, one that governs averages rather than certainties. The replacement of determinism by probability also changed the philosophy of measurement. In classical physics, measurement merely revealed pre-existing properties. In quantum physics, measurement participates in creating them. Before measurement, an electron does not have a definite spin, orientation, or position. It exists in a superposition. When measured, that superposition collapses to a definite state. The apparatus and the observer become part of the process. This raised deep questions. If observation is necessary for reality to crystallize, what counts as an observer? Must it be conscious, or can any physical interaction serve as a measurement? Different interpretations of quantum mechanics attempt to answer these questions in different ways. The Copenhagen interpretation, developed by Bohr, maintains that physical properties are undefined until measurement occurs. Quantum mechanics tells us only the probabilities of possible results. The many worlds interpretation, proposed by Hugh Everett Roman III in 1957, suggests that all outcomes occur, each in a separate branch of the universe. Thus, determinism is restored at the multiverse level, but lost within any single branch. The de Broglie-Bohm pilot wave theory posits that particles have definite positions guided by an invisible wave. While this restores determinism, it does so by introducing non-locality, a kind of hidden choreography of probability waves influencing matter. Each interpretation reflects humanity's struggle to reconcile intuition with mathematics. Yet all agree on one point: the classical deterministic world. You cannot describe nature fully. Reality at its foundation is probabilistic, whether that probability is seen as fundamental or as part of a hidden order. This shift also transformed technology. Devices that shape modern life depend on quantum probability. The operation of semiconductors in computers, the emission and absorption of photons in lasers, and the magnetic resonance used in medical imaging all rely on probabilistic transitions between quantum states. Even chemical bonds are stabilized by the probabilistic distribution of electrons around nuclei. Without accepting the uncertainty of the microscopic world, none of these technologies would function. More recently, engineers have begun exploiting probability itself as a resource. Quantum computers use qubits that can exist in superpositions, enabling parallel computation across many states at once. Quantum cryptography uses the uncertainty principle to guarantee secure communication. Any attempt to measure the quantum key disturbs it, revealing eavesdropping. These technologies show that the abandonment of determinism was not a loss but a liberation, opening new frontiers that deterministic systems could never reach. In the realm of philosophy and epistemology, the probabilistic framework challenges the idea that knowledge means certainty. Classical science equated understanding with prediction. To know was to foresee. Quantum science redefines understanding as the ability to describe likelihoods and constraints, not exact outcomes. Knowledge becomes relational and contextual, a map of probabilities rather than a script of fate. This change has resonated far beyond physics, influencing biology, psychology, economics, and even art. Complex systems theory, evolutionary models, and information science all embrace stochastic behavior as a source of creativity and adaptation. Consider the contrast between a deterministic and a probabilistic world, in human terms. In the deterministic model, every thought and action follows from prior causes. Free will is an illusion. In the probabilistic model, while probabilities constrain behavior, outcomes are not fixed. There is room for novelty, for emergence, spontaneity, and the unpredictable creativity that characterizes life. Thus, quantum theory has subtly reopened philosophical space for freedom and agency, though in ways that remain debated. Another profound consequence concerns time. In classical physics, time is a parameter that flows uniformly, linking cause to effect. In the quantum domain, temporal order can blur. Experiments in quantum optics have demonstrated delayed choice effects, where decisions made in the present seem to influence the past configuration of a system. These effects do not violate causality, but reveal that quantum events do not fit neatly into the linear arrow of time. Probability links past and future symmetrically through the wave function, suggesting that time itself might be an emergent phenomenon, not an absolute backdrop. From a broader cultural perspective, the shift from determinism to probability also reflects the modern human condition. The 20th century, marked by war, uncertainty, and rapid change, found in quantum mechanics a metaphor for the unpredictable nature of existence. Artists, writers, and philosophers drew inspiration from the idea that reality is open-ended, that observation alters meaning, that certainty is an illusion. The probabilistic universe became a symbol of both anxiety and liberation, the recognition that truth is not a single line but a spectrum. Yet amid these sweeping changes, one constant remains, Planck's constant itself, the small yet profound number that defines the scale of quantum effects. It is a reminder that even randomness has structure, that the universe operates with mathematical elegance, even in its indeterminacy. Each quantum of action, HHH, represents the minimum grain of physical reality, the indivisible unit of the universe's rhythm. It ties energy to frequency, motion to probability, and the infinite to the finite. To appreciate the philosophical magnitude of this, consider that determinism once gave humans the illusion of control. If everything was predictable, then knowledge could, in principle, grant mastery over nature. Quantum probability replaced mastery with participation. We are not external observers of a machine, we are participants in a process. Our measurements, our inquiries, our very existence contribute to how reality manifests. This participatory universe aligns with Planck's own humility when he said, "Science cannot solve the ultimate mystery of nature, because we ourselves are part of the mystery we are trying to solve." In modern quantum information theory, probability is even more central. The universe can be viewed as processing information, with entropy and uncertainty as fundamental measures of reality's richness. Probabilities are not signs of ignorance, but quantifications of information. Entanglement, once an oddity, now serves as a resource, a way to link systems across space and encode information in correlations. The probabilistic framework thus forms the bridge between physics and information, between matter and meaning. Even cosmology has absorbed this probabilistic spirit. The earliest moments of the universe, the quantum fluctuations during the Big Bang, are believed to have seeded the galaxies. Tiny random variations in energy density, amplified by cosmic inflation, produce the structure of the universe. Our very existence is the outcome of quantum probability writ large across cosmic time. What once seemed a philosophical abstraction has become a cornerstone of astrophysical reality. Despite its triumphs, the probabilistic worldview continues to provoke debate. Some scientists and philosophers still search for a deeper deterministic layer, perhaps in theories of quantum gravity or hidden dimensions. Others argue that probability is fundamental, that nature itself is woven from uncertainty. The question remains open, but the practical success of quantum mechanics leaves little doubt that probability is the most accurate language we have for describing the microscopic world. In the century since Planck's discovery, the intellectual journey from determinism to probability has reshaped not only science, but humanity's self-image. We no longer stand outside the universe as detached observers. We are participants in its unfolding, influencing it even as we study it. The universe is not a script written in stone, but a symphony improvised according to rules of harmony we are only beginning to grasp. To summarize the spirit of this transformation, classical determinism viewed reality as a closed chain of causes. Quantum probability views reality as an open field of possibilities. Measurement no longer discovers, it co-creates. Certainty is replaced by statistical law. Knowledge becomes the art of predicting likelihoods rather than certainties. Reality itself becomes participatory, relational, and dynamic. Thus, the classical deterministic view did not vanish. It was absorbed as an approximation within a deeper probabilistic truth. For macroscopic systems with vast numbers of particles, probabilities average out, and the old laws re-emerge. The planets still follow Newton's equations to extraordinary accuracy. Airplanes still obey deterministic aerodynamics. But beneath these smooth surfaces lies a restless quantum sea, a realm where certainty dissolves into possibility and where the universe, far from being a machine, reveals itself as an ever-unfolding mystery. In this realization, Max Planck's legacy reaches beyond physics. His discovery teaches a moral as much as a scientific lesson, that humility before nature is the beginning of wisdom. The shift from determinism to probability is not merely a technical change, but a transformation of world view, from control to participation, from rigidity to openness, from certainty to wonder. In the end, the quantum revolution reminds us that to know the world is to embrace its uncertainty. Reality, like music, derives its beauty not from predictability, but from variation, harmony, and chance. And so, through the vision that began with Planck's constant, we learn that the universe is not a clockwork but a melody, one that continues to play, probabilistically, in the grand concert of existence. When Max Planck introduced his revolutionary idea in 1900, he could not have imagined that a single letter H would come to symbolize one of the greatest turning points in human understanding of the universe. That tiny symbol known as Planck's constant, became the bridge between the visible and invisible worlds, between energy and matter, between certainty and probability. It is no exaggeration to say that without Planck's constant, quantum physics, and the modern technological world it inspired, would not exist. Planck's constant first appeared when Planck was studying the problem of blackbody radiation, how objects emit electromagnetic energy when heated. Experiments showed that the classical laws of physics, particularly those based on Maxwell's electromagnetic theory and thermodynamics, could not correctly predict the spectrum of radiation at high frequencies. According to classical physics, as the frequency of radiation increased, the energy emitted should have risen without bound, a prediction that became known as the ultraviolet catastrophe. Yet experiments showed the opposite. The intensity of radiation peaked and then fell sharply. To solve this paradox, Planck made a daring assumption. He proposed that electromagnetic energy could be emitted or absorbed only in discrete packets, not continuously. The energy of each packet was proportional to its frequency. E equals h nu E equals h backslash nu E equals h nu here. E is energy, nu backslash none, U nu is frequency, and HHH is the proportionality constant, Planck's constant. This simple equation changed everything. It suggested that nature, at its core, was quantized, that energy came in indivisible units, or quanta. The value of HHH, though incredibly small 126 times 10 minus 3, 146, 126 times 10 minus 34 126 times 10 minus 34 joule seconds, defines the scale at which quantum effects become significant. On everyday scales, HHH is negligible, which is why the world seems continuous and deterministic. But in the microscopic realm of atoms and photons, the smallness of HHH means that quantization dominates. Planck initially viewed his constant as a mathematical trick, a temporary hypothesis to fit experimental data. But within a few years, it proved to be the seed from which the entire structure of quantum mechanics grew. Einstein used HHH to explain the photoelectric effect in 1905, demonstrating that light itself consists of quanta, photons, each with energy E equals h nu E equals h backslash nu E equals h nu. Niels Bohr applied HHH to his model of the atom in 1913, showing that electrons could occupy only certain quantized orbits, where the angular momentum was an integer multiple of h/2 pi/2 backslash pi/2 pi, a quantity later called h-stroke or h bar. From that moment, Planck's constant became the universal measure of quantization, the heartbeat of the microscopic world. Every law of quantum physics, from Schrödinger's wave equation to Heisenberg's uncertainty principle, contains HHH. It is the thread that stitches together the probabilistic fabric of reality. In Schrödinger's equation, for example, HHH in the form of h-stroke governs how the quantum wave function evolves through time. It determines the wavelength of matter waves, linking momentum and wavelength through the de Broglie relation. Lambda equals h, p backslash lambda equals backslash frac h, p lambda equals ph. This means that every particle, not just light, exhibits wave-like behavior, its wavelength shrinking as its momentum increases. Without HHH, this duality of wave and particle could not exist. In Heisenberg's uncertainty principle, HHH sets the limit of precision with which we can know complementary quantities such as position xxx and momentum ppp. Delta x delta greater or equal to h4 pi backslash delta x backslash delta p backslash j backslash frac h 4 backslash pi deltax delta greater or equal to 4 pi, this inequality expresses the fundamental fuzziness of reality, a direct consequence of quantization. The uncertainty is not due to measurement flaws, but to the intrinsic quantum nature of matter. Planck's constant, small as it is, defines the boundary between the knowable and the unknowable. As physics progressed, HHH became the cornerstone upon which all quantum theories rested. In quantum, electrodynamics KED, the most accurate theory ever developed, HHH determines the quantization of electromagnetic fields. In quantum field theory, particles are viewed as excitations of underlying fields, and each excitation carries an energy proportional to h, nu/nu. Even in modern quantum, gravity, and string theory, where scientists seek to unify all forces, Planck's constant remains fundamental. It defines the smallest conceivable scales of length, time, and energy, the Planck length, Planck time, and Planck energy, natural units that describe the ultimate structure of space-time. Beyond physics, Planck's constant carries deep philosophical meaning. It represents the granularity of reality, the smallest tick of the universe's clock. Just as atoms reveal that matter is not continuous, HHH reveals that action, the product of energy and time, comes in quanta. The world is not infinitely divisible. There is a fundamental rhythm underlying existence. This idea shattered the illusion of smooth continuity that had defined classical science for centuries. Technologically, the implications of HHH are everywhere. The behavior of electrons in semiconductors, the emission of light in lasers, the stability of atoms, and the operation of quantum computers all depend on quantized energy levels determined by Planck's constant. Modern metrology, the science of measurement, even uses HHH to define the kilogram. Since 2019, the kilogram is no longer based on a physical object, but on a fixed numerical value of HHH, tying human measurement directly to the quantum fabric of the universe. The elegance of Planck's constant lies in its universality. No matter the system, atomic, molecular, or cosmic, HHH governs the smallest possible action. It tells us that nature's book of laws is written not in continuous ink, but in discrete letters. Every photon, every electron, every quantum leap carries the signature of HHH. It is the measure of how the universe quantizes itself. For Max Planck himself, the constant carried spiritual and philosophical weight. He believed that science revealed the order of creation, and that beneath all change and uncertainty lay a deep harmony. His constant, though born of pragmatic necessity, became the mathematical symbol of that harmony, a key that unlocked a new understanding of matter, energy, and mind. In a broader sense, Planck's constant teaches humility. It tells us there are scales of nature beyond our ordinary perception, and that even in the realm of absolute precision, there exists a fundamental limit. We cannot peer below HHH. It is the smallest unit of action, the whisper of the cosmos itself. Through this single constant, Planck connected all phenomena, from the glowing ember to the orbit of electrons, from the vibration of atoms to the curvature of space-time. It is no exaggeration to say that HHH is the foundation stone of the quantum world, a number that not only measures energy but defines the structure of reality. In the end, the story of Planck's constant is the story of modern physics itself, a story of curiosity, courage, and the willingness to challenge certainty. From the Blackbody furnace of 1900 to the quantum technologies of today, HHH continues to guide us through the unseen realms of nature. It is the quiet pulse of the universe, reminding us that even the smallest quantities can carry the greatest meaning, and that sometimes one number can change everything. The year 1900 stands as one of the great turning points in intellectual history. When Max Planck presented his now famous formula for Blackbody radiation to the German Physical Society in December of that year, few realized they were witnessing the birth of an entirely new vision of the universe. What began as an attempt to fix an anomaly in classical physics soon expanded into the quantum revolution, a movement that would transform not only science but also technology, philosophy, and the way humanity conceives of reality itself. Before Planck, the world of physics seemed almost complete. Newton's laws had unified motion and gravity. Maxwell's equations had united electricity, magnetism, and light. Thermodynamics had explained heat and energy. By the late 19th century, many scientists believed that only minor details remained to be filled in. The universe appeared predictable, continuous, and mechanical, an immense clock whose parts moved with flawless precision. Yet beneath this confidence lay cracks. Experiments with atomic spectra, the photoelectric effect, and blackbody radiation all refused to obey classical equations. Energy and matter behaved in puzzling ways when examined on the microscopic scale. The classical picture, where energy flowed smoothly and deterministically, no longer fit the evidence. Into this context stepped Max Planck. Working meticulously on the radiation problem, he found that no continuous model could match observation. To reconcile theory with experiment, he reluctantly proposed that energy could only be exchanged in discrete packets, quanta, proportional to frequency through the constant E equals h nu E equals h backslash nu E equals h nu. It was, as Planck later admitted, an act of desperation, yet it contained the seed of a revolution. Once that seed took root, nothing in physics was the same again. Planck's idea implied that nature itself was quantized, that at its most fundamental level, reality does not flow smoothly, but leaps from state to state. This broke the foundation of classical determinism. Instead of a universe where causes produced effects with perfect continuity, the quantum world appeared granular, probabilistic, and strange. The first to recognize the profound consequences was Albert Einstein. In 1905, he extended Planck's hypothesis to explain the photoelectric effect, showing that light is made of discrete photons, each carrying energy E equals h nu E equals h backslash nu E equals h nu. That insight earned him the Nobel Prize and proved that quantization was not merely a mathematical trick, but a physical truth. Soon after, Niels Bohr used Planck's constant to describe the structure of the atom. Electrons could occupy only certain quantized orbits, emitting or absorbing photons when they jumped between them. From these early steps grew a full-fledged scientific revolution. Between 1900 and 1930, the giants of modern physics Bohr, Heisenberg, Schrödinger, Dirac, de Broglie, Pauli, and others built upon Planck's foundation to create quantum mechanics, a framework that redefined the meaning of motion, matter, and measurement. The deterministic universe of Newton gave way to a world ruled by probabilities, wave, particle duality, and uncertainty. At the core of this new world, you lay Planck's constant. It appeared in every fundamental equation, setting the scale of quantum behavior and marking the threshold between the classical and the quantum domains. Without HHH, there would be no Schrödinger equation, no Heisenberg uncertainty principle, no atomic structure. Planck's discovery thus became the cornerstone of 20th century physics, igniting a revolution that extended far beyond laboratories. The consequences of the quantum revolution were profound. First, it redefined the nature of scientific explanation. In the classical era, scientists sought precise predictions. Given initial conditions, one could calculate exact outcomes. Quantum mechanics, however, replaced certainty with statistical laws. It did not say where an electron is, only the probability of finding it somewhere. For many, including Einstein, this was philosophically unsettling. He famously protested, "God does not play dice with the universe." Yet experiments consistently confirmed that the quantum world indeed behaves probabilistically. Second, the revolution reshaped our technological civilization. Planck's constant lies behind every modern electronic device. Transistors, lasers, solar cells, LEDs, and magnetic resonance imaging all depend on quantum principles. Quantum mechanics explains chemical bonding, semiconductor behavior, and even biological processes such as photosynthesis. The digital age computers, smartphones, the Internet exists because of quantum theory, a legacy that traces directly back to Planck's insight in 1900. Third, the quantum revolution expanded humanity's philosophical horizons. It forced thinkers to reconsider what it means to know something. Observation itself became participatory. In the quantum realm, measurement affects the system observed. Reality was no longer an objective, detached mechanism, but an interplay between observer and phenomenon. This challenged centuries of philosophical assumptions about objectivity, causality, and the nature of truth. Planck, though a conservative thinker by temperament, appreciated the magnitude of what had begun. He continued refining his ideas about energy quantization and encouraged younger physicists to explore them. His moral integrity and intellectual rigor set a standard for the new generation. In his later writings, Planck reflected that scientific progress often depends not on the sudden conversion of opponents, but on new generations who grow up familiar with the new truths. The quantum revolution proved him right. Within a few decades, it became the bedrock of all physical science. Moreover, the revolution did not stop at physics. It rippled through chemistry, explaining why atoms form stable molecules, through astronomy, illuminating the behavior of stars, and through cosmology, influencing models of the early universe. In the 21st century, it extends into quantum information science, where bits of information queue, bits exploit superposition and entanglement, phenomena rooted in Planck's constant. The emerging fields of quantum computing and quantum communication owe their existence to that original spark ignited by Planck. The quantum revolution also altered humanity's self-image. Classical physics had portrayed humans as spectators in a clockwork universe, governed by immutable laws. Quantum theory, by contrast, revealed a reality that is dynamic, relational, and partially indeterminate. We are not merely observers, but participants in an unfolding web of probabilities. This shift parallels revolutions in art, philosophy, and psychology that occurred during the same period: modernism, existentialism, psychoanalysis, all grappling with uncertainty and subjectivity. And yet, amid this radical change, Planck remained grounded in a belief that science reveals a deeper order. For him, the quantization of energy did not imply chaos but hidden harmony. He saw in it the fingerprint of universal law, the subtle rhythm of creation itself. That perspective infused the quantum revolution with a sense of wonder and reverence, a recognition that even the smallest quantum jump reflects the profound coherence of nature. By the time of Planck's death in 1947, the revolution he began had reshaped the physical sciences. It led directly to nuclear physics, condensed matter theory, and quantum field theory. It even provided the conceptual groundwork for later discoveries such as the Higgs boson and quantum entanglement experiments. Every subsequent generation of physicists has built upon Planck's daring assumption, pushing deeper into the quantum domain he first revealed. In retrospect, the quantum revolution stands beside the Copernican and Newtonian revolutions as one of humanity's greatest intellectual leaps. It displaced the certainty of mechanical causation with a richer, more mysterious picture of a universe built from probabilities and interactions. Through Planck's constant, the cosmos spoke to us in a new language, one that balances randomness with order, simplicity with depth. Thus, the phrase Planck's work ignited the quantum revolution is not a metaphor but a literal truth. From a single constant emerged an entire world view. The ripple that began in a Blackbody furnace spread across the vast ocean of knowledge, transforming every shore it touched. Science, philosophy, and technology continue to draw energy from that original spark. Today, as researchers probe the frontiers of quantum gravity and entanglement, they still walk the path Planck opened. Each experiment that tests the limits of reality pays silent tribute to the man who first dared to quantize the universe. His work did more than solve a scientific puzzle. It redefined what it means to understand. The quantum revolution he ignited remains an unfinished journey, inviting us to keep unraveling the fabric of reality, thread by luminous thread. Max Planck's introduction of quantization in 1900 did more than solve a problem in Blackbody radiation. It marked the beginning of a profound shift in our understanding of reality itself. Classical physics, grounded in Newtonian mechanics and Maxwellian electromagnetism, depicted a universe governed by absolute laws. Space was a fixed stage, time flowed uniformly, and causality linked past and future with rigid precision. Every event was the predictable consequence of prior states. Planck's quantum insight, along with subsequent developments in quantum mechanics, dismantled these assumptions, revealing a universe in which space, time, and causality are far more subtle and interwoven than classical thought had imagined. At the heart of this challenge lies the nature of quantum systems. Unlike macroscopic objects, which appear to follow continuous paths and well-defined trajectories, microscopic particles such as electrons, photons, and atoms exhibit behaviors that defy classical intuition. Their states are described by wave functions, mathematical constructs representing probabilities of position, momentum, spin, and other properties. The wave function does not confine a particle to a particular location or state. Instead, it spans a range of possibilities, blurring the boundaries of space. Only when a measurement is made does the particle assume a definite position, illustrating that space is not a rigid container but a context-dependent aspect of quantum reality. Similarly, time in the quantum domain is not as straightforward as in Newtonian mechanics. Classical physics treats time as absolute. Events occur sequentially along a uniform temporal axis. Quantum mechanics, however, shows that certain phenomena challenge this linearity. Experiments in quantum optics, particularly delayed choice experiments inspired by John Wheeler, demonstrate that decisions made in the present can influence how we describe the past state of a system. In Wheeler's famous thought experiment, photons passing through a beam splitter seem to decide whether they behaved as waves or particles based on measurements made after they traversed the apparatus. While causality in the sense of information transfer is preserved, no signal travels faster than light. The results suggest that temporal order in quantum systems is more nuanced than previously thought. The past present, and future are interrelated in ways that classical physics cannot account for. Perhaps the most dramatic challenge to classical thinking comes from entanglement, a phenomenon that Planck's quantization indirectly made possible to describe. When two particles interact and become entangled, their quantum states are no longer independent. Measurement of one particle instantaneously affects the other, regardless of the distance separating them. Albert Einstein famously derided this as spooky action at a distance, because it seemed to violate classical notions of locality. Yet numerous experiments, beginning with the tests of Bell's inequalities and continuing through modern quantum optics, have confirmed that entangled particles are correlated in ways that classical physics cannot explain. Entanglement highlights the profound interconnectedness of the universe. Space is no longer merely a backdrop in which events occur. It is part of the relational structure of quantum states. Two particles light years apart can exhibit correlations that suggest a deeper level of connectivity, one that is woven into the probabilistic fabric of reality. Classical ideas of separate, independently existing objects give way to a vision of the universe as a network of relationships, where separation in space does not imply isolation in influence. This interconnection also transforms our understanding of causality. In classical physics, causality is linear. Cause precedes effect, and one can trace an unbroken chain from initial conditions to outcome. Quantum mechanics complicates this picture. In entangled systems, the outcome of one measurement is correlated with another in ways that cannot be explained by pre-existing properties alone. Quantum correlations are non-local, and they force a reconsideration of what it means to say that one event causes another. Causality in the quantum realm is probabilistic, context, dependent, and fundamentally relational. Another way in which quantum theory challenges classical assumptions is through the concept of complementarity, introduced by Niels Bohr. Complementarity asserts that certain properties of quantum systems, such as particle-like or wave-like behavior, cannot be observed simultaneously. Which aspect manifests depends on the experimental setup. In other words, the attributes of a system are not intrinsic in the classical sense. They are defined in relation to the measurement. This challenges the classical idea that physical properties exist independently of observation, revealing that even seemingly simple concepts like position, momentum, or trajectory are contextually defined in the quantum world. Quantum mechanics also shows that the structure of space, time itself, may be influenced by quantum phenomena. While Planck did not live to see it, later developments in quantum field theory and quantum gravity suggest that the smooth, continuous spacetime of relativity may emerge from underlying quantum processes. Concepts like the Planck length derived from Planck's constant set a fundamental scale at which the classical notion of distance ceases to apply. At these scales, the geometry of space-time is quantized, and our intuitive understanding of space as continuous breaks down. The implications of these insights extend beyond physics into philosophy and epistemology. If space and time are not absolute and causality is probabilistic, then knowledge itself must be redefined. Observation is no longer a passive act, it is participatory. By interacting with a system, we bring certain aspects of reality into being. The universe is not a pre-written book with fixed chapters. It is a dynamic process in which possibilities are actualized through interaction. This has profound consequences for how we understand knowledge, objectivity, and the nature of existence. Furthermore, quantum theory emphasizes that the whole is greater than the sum of its parts. Classical reductionism assumed that understanding individual components of a system would automatically yield understanding of the system as a whole. Entanglement and non-local correlations demonstrate that this is not always the case. The collective properties of a system may exhibit behaviors that cannot be deduced from the behavior of isolated parts. Interconnectedness is fundamental, not emergent, and Planck's discovery of energy quanta opened the door to recognizing this deep relational structure. The challenge to classical notions of space, time, and causality is not merely theoretical. It has practical consequences in technology. Quantum entanglement underpins quantum cryptography, enabling secure communication channels that exploit the impossibility of copying quantum states without disturbing them. Quantum teleportation, quantum computing, and quantum sensors all rely on the understanding that spatial separation does not imply independent existence. These applications demonstrate that Planck's ideas, while abstract, provide concrete tools to reshape our technological landscape. Planck's work also inspires reflection on the limits of human intuition. Classical physics evolved to describe the macroscopic world of daily experience, where objects have definite positions and follow predictable paths. Quantum mechanics, by contrast, describes a reality that is counterintuitive, probabilistic, and non-local. Understanding this universe requires mathematical abstraction, conceptual flexibility, and openness to phenomena that defy everyday perception. Planck's courage in proposing quantization, despite its radical implications, exemplifies the willingness to challenge intuition in pursuit of truth. In conclusion, Planck's quantum theory shattered classical conceptions of space, time, and causality. It revealed a universe that is fundamentally interconnected, probabilistic, and relational. Objects are not isolated points moving through an absolute backdrop. They are parts of a network of probabilities, where measurement and interaction define reality. Time is not merely a uniform arrow. Past, present, and future are intertwined in ways that challenge linear intuition. Causality is no longer absolute but contextual, embedded in the structure of quantum correlations. Through Planck's insight, humanity came to understand that the universe is far stranger, more interconnected, and more elegant than classical physics could describe. The quantum world teaches us that at the most fundamental level, reality is not a static stage but a dynamic web of possibilities, a symphony of probabilities in which every particle, interaction, and measurement contributes to the unfolding of existence. Planck's discovery opened the door to this new understanding, igniting a revolution that continues to shape science, philosophy, and our conception of the cosmos. Max Planck's work in 1900 did not merely alter the course of theoretical physics. It also set in motion a chain of discoveries and applications that would ultimately transform human civilization. While his immediate focus was understanding Blackbody radiation and the nature of energy exchange, the principles he uncovered became the bedrock for an astonishing array of technologies that underpin the modern world. The ripple effects of Planck's constant quantization and the quantum revolution extend far beyond laboratories. They touch medicine, communication, computing, energy, and even the philosophical understanding of our place in the universe. At the heart of this transformation lies Planck's constant HHH, which dictates the quantization of energy in microscopic systems. The recognition that energy occurs in discrete packets provided a framework for understanding atomic and subatomic behavior. This understanding led directly to the development of quantum mechanics, the theory that describes electrons, photons, and atomic nuclei with extraordinary accuracy. Without Planck's foundational insight, the equations governing semiconductors, lasers, and nuclear processes would not exist, and the technological revolution of the 20th century would have been impossible. One of the earliest practical applications of quantum principles derived from Planck's work was in the development of electronics. Semiconductors, the basis of all modern electronic devices, operate on the principles of energy quantization and electron behavior within atoms. The behavior of electrons in a semiconductor, how they jump between discrete energy bands, is explained entirely by quantum theory. Without Planck's foundational insight, engineers would have no way to understand or manipulate these energy levels. Every computer, smartphone, and microchip owes its existence to the chain of discoveries that began with Planck. Lasers are another direct consequence of Planck's quantum insights. The principle of stimulated emission, which forms the operational basis of lasers, relies on the idea that electrons occupy discrete energy levels and can be induced to release photons of a specific energy. Lasers now serve a multitude of functions, from precise surgical procedures and medical imaging to fiber optic communications and barcode scanning. These devices exemplify how a fundamental understanding of quantum energy leads to tangible benefits for society. Planck's work also reshaped medicine through technologies that rely on quantum mechanics. Magnetic resonance imaging (MRI) depends on nuclear magnetic resonance, which in turn relies on quantum properties of atomic nuclei in magnetic fields. PET scans, X-ray lasers, and even the understanding of molecular structures in pharmacology all derive from the precise description of energy levels and quantum transitions. These medical technologies save lives daily and illustrate the profound societal impact of Planck's theoretical breakthroughs. The influence of Planck's discoveries extends into energy and materials science. Solar cells, which convert sunlight into electricity, operate on the photoelectric effect first explained by Albert Einstein using Planck's quantization principle. Photons excite electrons in discrete steps, allowing energy to be harvested efficiently. Similarly, the development of superconductors, semiconducting polymers, and quantum dots relies on the understanding that energy is not continuous but quantized. Planck's work provided the conceptual tools to design materials with unprecedented precision, fueling innovations in renewable energy and nanotechnology. Beyond individual technologies, Planck's discoveries reshaped the scientific method and the relationship between science and society. Classical science emphasized determinism, predictability, and a linear cause and effect understanding of the universe. Quantum mechanics, emerging from Planck's insights, replaced these certainties with probabilities, uncertainty, and complex interrelationships. This shift required society to rethink the limits of knowledge and the role of experimentation. Scientists no longer simply observed nature. They interacted with it, understanding that measurement itself influences outcomes. This participatory aspect of science has philosophical and ethical implications for how we conduct experiments, interpret data, and apply technology responsibly. Planck's discoveries also catalyzed the development of computing and information technology. Quantum mechanics allows for the precise manipulation of electrons and photons in ways that classical physics could not predict. Transistors, the building blocks of modern computers, depend on quantum principles to control electron flow. Without the quantization of energy, electronic circuits would fail to function predictably. More recently, quantum computing has emerged, exploiting superposition and entanglement to perform calculations beyond the reach of classical machines. These cutting-edge technologies are direct descendants of Planck's foundational work, demonstrating that a single theoretical insight can generate decades of technological evolution. The societal impact of quantum technologies extends into communication and security. Quantum cryptography leverages entanglement and quantum uncertainty to provide unbreakable encryption, while quantum teleportation and quantum networks are beginning to redefine global information transfer. These advances promise to revolutionize how governments, corporations, and individuals handle data securely. Planck's work, though abstract and theoretical in its origin, underpins these very real societal benefits, highlighting the profound link between pure science and practical outcomes. Equally important is the cultural and philosophical influence of Planck's discoveries. By challenging classical determinism, his work reshaped humanity's understanding of reality. Concepts such as uncertainty, probability, and entanglement have permeated not only physics, but also philosophy, literature, and art. Writers and thinkers draw on quantum ideas to explore themes of ambiguity, interconnectedness, and the limits of knowledge. Science, as Planck's work demonstrates, does not exist in isolation. It informs and transforms the broader cultural and intellectual landscape. Planck's contributions also fostered an international scientific community. Quantum theory demanded collaboration among physicists across borders, including Einstein in Switzerland, Bohr in Denmark, Heisenberg in Germany, Schrödinger in Austria, and Dirac in England. The global effort to understand and apply quantum principles set a precedent for international scientific cooperation. Today, projects like CERN, LIGO, and Global Quantum Communication Networks continue this tradition, illustrating the enduring societal value of foundational scientific research. Finally, Planck's work underscores a broader lesson about the relationship between theory and application. Many of the technologies we take for granted, computers, lasers, medical imaging, renewable energy solutions, arose not from an immediate practical goal, but from a theoretical breakthrough in understanding the fundamental nature of energy. This demonstrates the profound importance of basic research. Insights that initially seem abstract or purely academic can, decades later, revolutionize the way humans live, communicate, and interact with their environment. In conclusion, Max Planck's discoveries laid the groundwork for a technological and societal transformation that continues to unfold. By revealing the quantized nature of energy, he opened the door to quantum mechanics, which in turn enabled modern electronics, lasers, medical imaging, quantum computing, and secure communication technologies. Beyond the practical applications, Planck's work reshaped the scientific world, emphasizing probability, interconnectedness, and the participatory role of observation. Society has not only benefited materially, but has also been intellectually enriched, gaining a deeper understanding of the subtle, intricate, and interconnected fabric of reality. Planck's legacy demonstrates that profound theoretical insight can ripple outward to transform every aspect of human civilization. The quantum revolution he ignited reminds us that science, even at its most abstract, is inseparable from society, culture, and technology. The tiny constant HHH, introduced to solve a simple problem in Blackbody radiation, became the cornerstone of modern life, illustrating that understanding the universe at its most fundamental level has consequences far beyond the laboratory. Through Planck, humanity learned that knowledge is not only a pursuit of truth, but also a catalyst for progress, creativity, and societal transformation. Every modern innovation that relies on quantum principles stands as a testament to the enduring power of his insight, demonstrating that foundational science can reshape the world in ways the discoverer could scarcely have imagined. Max Planck's introduction of energy quantization in 1900 marked the beginning of a scientific revolution whose effects continue to resonate more than a century later. While his initial work focused on a specific problem in blackbody radiation, the principles he uncovered became the foundation of quantum mechanics, the most successful theory of the microscopic world. Beyond its immediate scientific impact, Planck's work has inspired generations of scientists, reshaped philosophical perspectives on reality, and set humanity on a path of technological and conceptual exploration that remains ongoing. Planck's influence begins with the scientific inspiration he provided. His courage in proposing quantized energy at a time when classical physics dominated set a precedent for bold theoretical innovation. By challenging the established assumptions of determinism and continuity, Planck demonstrated that scientific progress requires both rigorous calculation and imaginative daring. Young physicists, witnessing the success of his ideas, recognized that theoretical courage could unlock deep truths about nature, even when those truths defied intuition. Figures such as Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac all built upon Planck's foundation, taking his initial hypothesis and developing it into the comprehensive framework of quantum mechanics. The scientific legacy of Planck's constant HHH cannot be overstated. Every calculation in quantum mechanics, from energy transitions in atoms to the behavior of subatomic particles, relies on this fundamental constant. It governs phenomena such as the photoelectric effect, electron orbitals, quantum tunneling, and particle-wave duality. Planck's insight provided the language and structure necessary for later discoveries, including quantum electrodynamics, quantum chromodynamics, and modern quantum field theory. In effect, Planck provided a set of rules for understanding the microscopic universe, rules that scientists continue to apply and expand today. Moreover, Planck's work has reshaped the culture of scientific research. His method combined meticulous experimentation with deep theoretical insight. He was willing to explore ideas that initially seemed radical, yet he grounded them in empirical evidence and mathematical rigor. This combination of imagination and discipline became a model for modern physics, encouraging researchers to pursue bold hypotheses while maintaining methodological integrity. The quantum revolution he sparked serves as a constant reminder that the most transformative discoveries often arise from careful attention to anomalies and willingness to question long-held assumptions. Planck's discoveries also influenced the philosophy of science. Classical physics portrayed a universe governed by predictable laws, where knowledge of initial conditions allowed precise prediction of outcomes. Quantum mechanics, emerging from Planck's insight, replaced certainty with probability, continuity with quantization, and separability with entanglement. These shifts have profound philosophical implications. Scientists and thinkers have had to grapple with the limits of determinism, the role of the observer, and the participatory nature of measurement. Planck's work thus bridges physics and philosophy, encouraging reflection on the fundamental nature of reality and the role of human understanding in shaping it. The inspirational impact on generations of scientists is evident not only in physics but across disciplines. Chemists rely on quantum principles to understand molecular bonds. Biologists apply quantum mechanics to processes like photosynthesis. Computer scientists explore quantum algorithms that promise unprecedented computational power. Planck's initial insight into discrete energy packets has become a universal tool, inspiring researchers to explore new frontiers in information, materials, and energy science. The principle that deep understanding of fundamental laws can lead to revolutionary applications motivates scientists in diverse fields to pursue theoretical and experimental research with courage and creativity. Another key aspect of Planck's legacy is the technological transformation enabled by quantum theory. Technologies that define modern life, semiconductors, lasers, LEDs, magnetic resonance imaging, quantum computers, and secure communication networks, owe their existence to principles first revealed through Planck's work. By demonstrating that energy is quantized and that matter obeys non-classical rules, Planck laid the groundwork for innovations that have reshaped medicine, computing, communications, and energy production. These technologies exemplify how fundamental scientific insight can ripple outward, profoundly affecting society. Planck also inspired international collaboration and the growth of scientific communities. The challenges and opportunities presented by quantum theory drew scientists from around the world into shared research programs, conferences, and collaborative publications. The emergence of quantum mechanics created a global scientific dialogue, encouraging cross-cultural collaboration and fostering an environment in which the best minds could challenge, refine, and expand upon one another's ideas. This collaborative spirit remains a hallmark of modern science and a testament to Planck's enduring influence. His influence extends into education and mentorship. Planck not only produced groundbreaking research, but also nurtured future physicists through teaching and guidance. His clarity of thought, rigor, and ethical standards set an example for students and young scientists, emphasizing that the pursuit of knowledge carries both responsibility and humility. The tradition of mentorship he inspired continues today, as physicists encourage the next generation to question assumptions, explore anomalies, and seek fundamental truths. Planck's discoveries also have a cultural and societal resonance. By revealing a universe that is probabilistic, interconnected, and participatory, he challenged humanity's understanding of existence. Concepts such as uncertainty, duality, and entanglement have influenced philosophy, literature, and art, inspiring new ways of thinking about reality and human experience. The quantum world, has become a metaphor for complexity, interconnectedness, and the limits of human perception, illustrating the broad cultural impact of Planck's scientific contributions. Looking forward, Planck's influence continues to shape the frontiers of physics. Researchers in quantum computing, quantum communication, and quantum gravity build directly on principles that emerged from Planck's work. Experiments with entanglement, superposition, and quantum coherence aim to unlock new technologies and deepen our understanding of space, time, and matter. Even in cosmology, concepts such as Planck's, scale physics, and quantum fluctuations in the early universe trace their intellectual lineage to Planck's insights. He provided not only tools for solving immediate problems, but also a conceptual framework for exploring the unknown. Finally, Planck's legacy embodies a timeless lesson for human understanding. His work shows that profound discoveries often arise from careful observation of anomalies, combined with the courage to propose revolutionary ideas. It demonstrates that fundamental science, even when abstract and theoretical, can reshape our world technologically, philosophically, and culturally. Planck's discoveries remind humanity that curiosity, rigor, and bold thinking are essential to progress, and that each generation builds on the foundations laid by those who dared to see the universe differently. In conclusion, Max Planck's discoveries inspired generations of scientists and continue to shape the future of physics and human understanding. By introducing the concept of quantized energy, he laid the foundation for quantum mechanics, revolutionized the understanding of matter and energy, and enabled the development of transformative technologies. His work reshaped philosophical thinking, encouraged scientific collaboration, and demonstrated the profound societal value of fundamental research. Beyond the laboratory, Planck's insights have influenced culture, education, and the collective imagination, creating a legacy that bridges science and society. Planck's life and work exemplify the power of human curiosity, intellectual courage, and the pursuit of truth. Through the discoveries he initiated, humanity has gained not only new tools to manipulate the physical world, but also a deeper understanding of the universe and our place within it. The quantum revolution that he sparked continues to evolve, and the scientific, technological, and philosophical journey that began with Planck's constant is far from complete. His legacy endures as a guiding light, inspiring present and future generations to explore the universe, question assumptions, and embrace the profound mysteries that define reality.